Hello, Professor Zhang. Your report is wonderful and amazing, and inspired me a lot. Frankly speaking, my research mainly focuses on 3D bioplating bone tissue engineering. It's completely different from 3D alloy plating.
Okay,
Generally,
yeah,
the collagen as the bioink and then and some nanoparticles to increase mechanical strength. For example, we under HAP and so biocompatibility compatibility is not a big problem for us, but the improvement of the mechanical strength is a headache. Interestingly, this is just the opposite of your concern about, and I think the mechanical strength should be absolutely no problem for you. So my question is, how do you balance mechanical strength and biocompatibility through the design of materials structure?
okay, thank you. So, Professor Shaw, so this is a very great question. So
Mm,
basically, we will use the biomedical titanium alloys, for example. If we use the materials of beta titanium alloys, there should be no problem for the biocompatibility because there's a lot of these that's being investigated and reported for example, for beta
I
titanium
see.
alloys. So then we will select the titanium alloys, and then we will use this kind of to produce the structures, and that will be good for this thing. For example, if we go to I know the two
Mm,
places. There's just one license. It's one is a Fuzhou, so Chinese Academy of
mhm,
Sciences of the matters of Fuzhou is a one Chinese Academy of Science
mhm,
institution. So of course the professor Lin Jinxing, so he has been
mhm,
licensed for the use of 3D printing of titanium alloys. That's because just use the beta titanium or titanium, they have been proved.
mhm,
So that's have a
mm,
good biocompatibility. So then we use 3D printing to produce the structures for plants,
mm,
for specific
mm,
plants. And these things were very important to build the structure. So that's why for this kind of case, first thing we select the material with good compatibility, and then we should worry about the strength. So that's why I use 3D printing. We should use the structures. So which kind of material should have enough or sufficient
mm,
making the properties of course the fatigue life. So another
okay.
institution is the Shanghai Jiaotong University. So that is the one hospital, the ninth hospital. So that's why for
Mm,
these things, they also they are very happy to see the structures with the structure of this. So that's the things they want to know because this one we put human beings in the structures.
yeah.
They want to know the structures with the structure with a particular life. That's why when they see this kind of structure, they want to put the hip for a hip cup or any place for a hip burn. This one can be produced in a lot of things. So that's why they're very keen to know the fatigue life and the structures, whether suitable, not suitable to the human being as a plant for long-term using.
Genius idea. Yeah. Yeah. Can some metal elements cause toxicity?
Uh,
For example, not because it's not pure titanium. So some other metal elements cause biotoxicity.
yeah, good question. So for this thing, the element of toxic is one very big issue for that. So because the thing is, we mention these things in the Progress in Material Science article. So we have one session to mention
Mhm.
the toxic of the element from different element. So, but the one thing is that we say we try to use the material for first stage. We selected the materials with a good biocompatibility. So of course, this has been proved by license. Okay, this is
Mhm.
very important because license is very important for everyone to use. Even we can produce, if this was a low license, it's very hard to be used in clinic. So there's no
Mhm.
way for this. That's why for the first stage, so we need to find the materials suitable. For example, Ti6 aluminum for vanadium. This is fantastic, and this is ongoing used for more than 60, 70 years. Okay, of course, this one is a still dominant one for the metal implants in hospital. So it's about this one is proved there's no problem for cleaning everything by capability. So it's about for us, we just use the material with the suitable or approved compatibility, then we can
Mm-hmm.
produce a structure for different applications. For example, use a medible or use a hip or use a face or head or
Mm-hmm.
scar, anything we can use. This can save a lot of time for the clinic license in
Mm-hmm.
hospitals.
Oh, I got you. Yes, yeah, that's wonderful. I have a last question. Uh, how can you predict their survival life? Because the implants to fill in body fluid environment. So how can you verify and predict their survival life?
Uh, that's a good question. We didn't produce parts because we first thing we my research mostly was step by step. We were not trying to go that far first because we should care about the biomechanical property for this thing first. So because this is the most
Mm,
important for biomechanical property, that means it's a biocompatibility, and also we should have enough mechanical property. That's because of for the fatigue life energy, and we should also check for the corrosion behavior. This then we further we go to the fluid things. So I think the Professor Chen
mm,
has one or two publications. So we produce for the dynamic fluid inside in the corrosion behavior of the dynamic fluid. So I think this is one way we can prove a little bit,
mm,
but I think this one
mm,
should do further work. But it's a good question for the verify the fluid of the body fluid or other fluid in the structures. But I think the one we should not problem because the one way because the size of the burns, so of the
mm.
the pores inside, the the size of the pores roughly from 200 to 500 micrometers,
Oh,
and
200.
also somewhat big. That's why for us we could enough because these structures, when we produce these things in the real parts, they the unit cell could be scaled up or scaled down to match the size. So that means we can do anything here. So we can this kind of size we can produce. For example, you
Mm,
produce the skull, we can scale up or scale down. They make smaller, make it bigger. So that's why for these
mm,
things, for example, we try to make these things this size.
mm.
There's a lot of things make us put it all together. They can make smaller. We can fill in the medible, make a human or any parts of our human body beings. So that's why this can match the size of the pores of human beings. So roughly 200 to 500 micrometers. So should be fine for the body fluid to transport inside.
Oh, yeah. Yeah, that's all. Yeah. Thank you so much. Yeah, thank you so
No
much.
worries. But thanks for your good question. This question all great. It's very inspiring. Yeah.
Okay, okay.
Any questions from our colleagues and audience?
Any questions?
Yeah, please.
Yeah. Uh, Dear Professor Zhang, uh, how do you think about the future of the 3D printing biomedical titanium alloys? Because the biomedical titanium alloys may be service modified before it's implanted into the human body. And do you have any opinions in its applications in the industry field?
Okay, thank you. This is a great question. So actually, for 3D printing of biomedical applications, I think this is very clear for these things. And this one, there's a lot of economic benefit from, especially from Shanghai Jiaotong, the Ninth Affinity Hospital. They make a lot of money every year. They just produce the thing. So that's one way. If we just consider for the parts as where Professor Shaw's metric for the other thing. So that's the one produce the parts. It will produce the parts from new alloys. That will take ages for implant. So I think the best way, and this is practical and it is also functional for the hospital. So they produce the parts from the approved alloy. For the approved alloys in hospital is stainless steel, 316L stainless steel, and also CP titanium, titanium 6 aluminum for vanadium. That's it. And of course, cobalt, chromium, tungsten. So that's all for the few types of the metal materials in hospital is approved. So that's what for 3D printing is really the future for these things because of the aged population is increasing every year. And even in China, it's even worse for this situation. So that's why for this in the hospital, this is the one way we can use 3D printing as a method to produce the approved alloy composition to match the performance or customized structures. That is a fantastic, and this is very, very practical. That's why for hospitals, I know for a few of these things, they make a lot of money. It's better for Shanghai Jiaotong University, Ninth Affinity Hospital. They make a lot of money not because they just use this one, produce titanium 6 aluminum vanadium for different parts for patients. So that's why for these things, it's a very good thing to make a customized implant for human beings, especially for those people who have big issues with shoulders and the knees and the hips and also some other place. So this one, no doubt, is the one of the dominant field in the future. And also this is also making a lot of money on these things. But if you want to try to produce this as a new alloys, I believe this is a big challenge. So because the first thing from the hospital, so this first thing should approve, get the license of the material to be used. For a new material, so from design, produce, research, and finally get approved, that's at least will take 20 years because you do a lot of things to understand the fatigue, corrosion, biocompatibility, and also clinical trial, and also a lot of animal, and so many of these things. So, but even after 20 years, even any step, there's a mistake or something wrong, the whole design will be invalid. So that's why for 3D printing, we treat this one as a method to produce the structure from approved licensed material. That will be one very, very main road for commercialization of the 3D printing of the biomedical material.
Okay, thank you very much for these questions. That's all my questions.
Okay, thank you.
Okay, thanks. BME Horizon gives us this platform to discuss the 3D printing of biomedical titanium alloys as well as other related questions. Thanks for Professor Zhang's lecture and Professor Shaw's brilliant discussions. Thanks everyone for attending. Jenny, is there anything else you would like to add?
Thank you, professors, and thank you all for today's sharing. And also thanks everyone once again for joining us today. We hope you found the sessions insightful and value. And also please feel free to reach out if you have any questions or would like to learn more about our journals. We look forward to your continued attention for BME Horizon. Have a nice day and enjoy your weekend. Thank you.
Thank
Yeah,
you.
thank you very much. Thank you.
Thank you.
Yes,
Bye.
Thank you.